Again, you could try these on your own to see if you can get the hang of it and come back to the video when you're ready, but we'll just go through this together. So E2 versus SN2, I have methoxide as my first reagent here. Methoxide is very reactive, has the negative charge. So don't have to worry about this methanol that's also in the reaction. That's just going to be our solvent. If you have something that is negatively charged, that's going to be the thing that dictates the reaction. It's going to do some attacking. It's either going to attack the backside to do SN2, or it's going to attack to the beta hydrogen to do E2. Okay, so looking at the reactivity of the reagent, it's both a strong nucleophile and a strong base. So something's getting attacked here. It's either going to be strong nucleophile means Sn2 mechanism, or strong base means it's an E2 mechanism. Okay, so when we have methoxide or T-butoxide, let's look at the other ones that are similar to this, right? Here's ethoxide. Every single one of those are going to be my choices. Those are going to be my choices. Any others? Hydroxide. There it is. Those are our strong bases, strong nucleophiles, strong bases. So every one of these are capable of doing both the SN2 and the E2. So let's go and just label each of these SN2, E2, and that was the last one. Strong nucleophile, strong base. Okay, now compare that. So remember, hydroxide, alkoxide. All right, what do the other other reagents look like? Here we have a neutral amine. Neutral amine, that is a strong nucleophile, meaning it loves to do the SN2, but it is a weak base. It is not one of our strong bases. So we typically are not going to see ammonia or a small amine like this doing elimination. It would prefer, if it can, if it's possible, it's going to do the SN2. It's going to do the backside attack. Okay, let's look at these other anions. So NaN3 minus, N3 minus is called a ZID. It's called a ZID. Down here we have cyanide, NaCN. This is called cyanide. And NaSH, we have SH minus. You don't have to worry about the name of that guy. These are all excellent nucleophiles, but they are not strong bases. They are not strong bases. Okay, so each of these is going to be a strong nucleophile, so it'll do SN2. But it is a weak base. Strong nucleophile, SN2, but not E2. Because it's a weak base. So just like ammonia, so we could kind of put a little note here. So ammonia has the same general reactivity as a ZID and cyanide and SH minus. Strong nucleophile, but a weak base. So SN2, fantastic. E2, no, because it's not a strong base. Not a strong base. So what's critical is that you recognize the reactivity of your substrate on whether or not you have a strong base, because only when you have a strong base is E2 going to be your consideration. E2 going to be an option. Okay, so now let's take a look at these and decide which one is going to be favored. Now what we have to do is we have to look at our substrate and think about the carbon that the leaving group is on, and to decide what mechanism is going to win if we have a competition. So for example, when we have methoxide here, SN2 is possible, E2 is possible. So we take a look at our substrate. We have a leaving group, right? This is called a tosylate. Tosylate is a great leaving group. But what kind of carbon is it on? It is on a methyl substrate. So can you do an E2 elimination when it's methyl? You cannot, because I don't have a second carbon to make a double bond. So this is going to be 100% SN2 piece of cake, 100% SN2. So instead of having a tosylate, I now have my methoxy group is my nucleophile. That's what's going to add on to my methyl group. I realize I have two methyl groups here. So this carbon, let's point this out. This carbon is the one that's getting attacked for my backside attack. And that's this carbon right here if we want to kind of track it. So we could show our mechanism, just as a little reminder here. How do we get that? Backside attack, attack the carbon and then kick off the leaving group. That CO bond gets broken. So I get a substitution, SN2, SN2, all the way. All right, and how about our next one? Also SN2, why? Because it's a weak base, because ammonia is a weak base. So this is also SN2. And so our awesome amine, awesome nucleophile attacks the carbon, kicks off the leaving group. Okay, we have some stereochemistry here. So what does our product look like? If our leaving group is a dash behind the plane, our nucleophile has to come from the front. So it's going to end up as a wedge, and we'll add the NH3 group. Now NH3, this nitrogen now has 4 bonds, and no lone pairs has 4 bonds. A nitrogen with 4 bonds, 1, 2, 3, 4, 1 electron for each bond. Nitrogen wants 5 normally. So if you are short an electron, this is an N+. So that's how good of a nucleophile amines are, or ammonia. So good that it's going to do a backside attack even if it gives it a positive charge in the end. Okay, now you might see sometimes that if they say there's NH3 excess, if you have an excess of this reagent, you can actually use that to deprotonate. You could use that as a base. A weak base can deprotonate, and so sometimes you'll see this product as the neutral product. That is not a good looking carbon chain. So really you can kind of draw this product, this SN2 product, either way. You'll often see it in one representation or the other, either as the ammonium group or the neutral amine. All right, let's look at our next example here. Our next example, we have we now are dealing with alkoxides, which are strong nucleophiles and strong bases. So now we have to, this is our first example where we have SN2 possible, E2 possible. Who's going to win? Who's going to win? For that, we have to look at the carbon bearing the leaving group, and they're the same substrate in each case. We have a secondary leaving group. And so with a secondary leaving group that has just enough steric hindrance so that who wins? Elimination wins, E2. E2 wins. So they're both going to be elimination. We're going to get an alkene product. But notice in this first case, we have a bulky base. So that's going to be described as Hoffman elimination. And the other one, we have a non-bulky base. So anything other than t-butoxide, methoxide, hydroxide, ethoxide, propoxide, anything other than t-butoxide, we're going to get our ordinary elimination, which is described as Zaitsev. So what do those look like? With the Hoffman, with the big bulky t-butoxide, where does it go? It's going to go to this position. It's going to go to the less substituted. Right? If we think about, we have 2 beta positions here. That's the decision we're making, Hoffman versus Zaitsev. It's different regioisomers, different regions or sites of the molecule can be attacked. And so with t-butoxide, it's going to attack the less substituted position to give what? The less substituted alkene. The less substituted alkene is the major product. We call that the Hofmann product. Okay, but if I use any other base, then I get my normal alkene, my normal elimination, E2 elimination. And we call that Zaitsev, and that what that means is it goes after the more substituted position. It goes after the more substituted proton. So now my strong base comes in and attacks here. Now notice, I have to do a rotation here because there's only one beta hydrogen at that position, and right now they're not anti. So I can't do my elimination mechanism yet because these are not anti. So I need to rotate. This one is a little trickier than I thought. Okay, so so before we draw the Zaitsev product, we have to rotate. And it doesn't matter which one we rotate. I meant to do it the other way, but that's okay. Let's keep the first carbon the same. Let's keep this one fixed, and let's rotate the other one down, because that will make the bromine a wedge. So there's a lot of different ways you could draw this. Remember, I did the example where I put the hydrogen in the plane and the bromine in the plane. You could do that as well, but this one requires a little less work. I could just rotate to put now the bromine is a wedge and the hydrogen is a dash. So now they are anti. So now I could show my base come in and eliminate. Do my E2 elimination, 3 curved arrows. And so what is that? Give me the more substituted alkene product. And I'm only going to get the one where the ethyl group is opposite the methyl group, because I have to do this anti-elimination. So whether this is more stable or less stable, this is what I end up getting. So I get the more substituted alkene. The more substituted alkene is the Zaitsev. All right. How about the next one? We already looked at our nucleophile. A Z is not hydroxide. It's not an alkoxide, so it's not going to be competing with E2. It's just going to be a straight out Sn2. It's just going to be an Sn2. And is Sn2 allowed? We're at a primary position, right? So Sn2 looks great, except do we have a leaving group? Uh-oh. Hydroxide is not a leaving group. So remember, we need bromide, chloride, iodide, or maybe tosylate as an example here. So if I try to do an alcohol and didn't turn it into a good leaving group somehow, what happens? No reaction. No reaction. So without a leaving group, no leaving group. Without a leaving group, nothing happens. Thought I'd sneak that one in there. Okay. All right, how about our next one? Hydroxide can do Sn2 or E2 because it's a strong nucleophile and a strong base. What kind of leaving group do we have in this case? What type of carbon is on a tertiary position? I have a tertiary leaving group. So how does that look for backside attack? Tertiary leaving group, how does that look for backside attack? No way. So what's going to win? E2, landslide win, landslide win. Okay, so what we have to decide though is we have this is a beta position, this is a beta position. There's 2 different alkenes we can get. Are we going to get Hofmann elimination or Zaitsev elimination? Unless we're using T-butoxide, we're getting Zaitsev. We're getting Zaitsev. So we're going to, we're going to eliminate from one of these side positions. That's going to put the double bond on the inside of the ring. And what about the methyl group? Is it still a dash? This is a common mistake. Is it still a dash? What do you think about that? No, because an alkene, remember, is planar. So every time we do an elimination reaction, we flatten out the groups on those two carbons are going to be planar. So there's no dash or wedge there. So we get our Zaitsev product, more stable, more substituted. Okay, I didn't have to worry about stereochemistry here because we had a CH2, right? We have a CH2, and so you can take, we definitely have a beta hydrogen available, so we could just use that one. Sorry, my Apple Pencil's starting to freak out. So we would get our alkene like this. All right, looking good. And our last two reactions are just going to be backside attack rather than E2. Why? Because we don't have a strong base. So the only time Sn2 and E2 are competing is when we have some strongly basic reagent like hydroxide or alkoxide, methoxide, ethoxide, T-butoxide, something like that. Okay, so can backside attack happen? Can backside attack happen? What kind of leaving group do we have here? We have, it's on a primary carbon. They have a primary leaving group. So that looks great. So cyanide can attack the carbon, kick off the leaving group, attack the carbon, kick off the leaving group. There's no stereochemistry to worry about here. So you could just write it in the same position that the chlorine was. You can't observe the backside attack here. Okay, I should note here that we have a whole bunch of interesting solvents here: DMSO, acetonitrile, acetone. These are all solvents that DMF. These are solvents we might find being used in a reaction. Those are all called polar aprotic solvents. By the way, we're going to have another lecture on this. This is called a polar aprotic solvent, and that's actually great for the Sn2. This is ideal for the Sn2. So notice I never looked at the solvent in any of these cases to make my decision. So our decision is going to be based on factors other than the solvent. But just FYI, if we really want to furthermore favor the Sn2, we could use a solvent like one of these that's polar aprotic. Okay, so we have, again, this sulfur anion is very large anion, so it's an awesome nucleophile, but it's also stable in terms of basicity. It's a weak base, so it's not going to do elimination. But here I do have a stereocenter where when I do my backside attack, I'm going to observe that backside attack. So so notice my bromine is pointing in a down position. And so when I draw my product, get some practice drawing those chairs. Oh, that one came out pretty good. That was pretty lucky. I usually have to redo it a few times. So what would that backside attack look like? What would that backside attack look like? I would now, the sulfur had to come from the up position, which at that position is in the axial position. So think about it. If you drew it as a hexagon, I have a methyl up and a bromine down. So this actually isn't a chiral carbon, but it is a molecule that has stereoisomerism because the methyl and the bromine are trans to each other. But when I do that backside attack, the methyl and the sulfur are going to be cis to each other because I can see that backside attack. So just kind of want to point out what that looks like. And again, we could observe that inversion of stereochemistry. There's a hydrogen here pointing up, and now the hydrogen is pointing down. Remember that, like, backside attack, we get that flipping of the umbrella effect there. So just wanted to have a try and give you a variety of substrates, a variety of nucleophiles to work with. But after this lesson now, you should know everything there is to know about the E2 elimination, the requirements that you have a strong base and a good leaving group, and how do we predict the stereochemistry when that's relevant, making sure the leaving group and the beta hydrogen are anti to each other. How do we determine the regiochemistry? Well, that's going to depend on the type of base we're using, either Zaitsev or Hofmann elimination, a more substituted or less substituted alkene, on whether or not we're using a bulky base. And then finally, how could we tell that an E2 reaction is going to happen at all when sometimes an Sn2 mechanism is favored instead? And so that that depends entirely on when we have a base slash nucleophile, when we have something that's capable of doing both the Sn2 and the E2, then it's all about steric hindrance. And it's only when we have, sorry, did we have any examples? We didn't have any examples. E2-1 in every case here. It was only on the page before that we saw an example where the Sn2-1, it's when you have a primary leaving group. When you have a primary leaving group, that's when Sn2 is going to be major. So it was funny, in our Sn2 versus E2 worksheet, they all ended up being E2 when the competition happened. But that's a good lesson. E2 is really, really favored because Sn2 is going to happen only when there's no steric hindrance whatsoever. And that's in the case for a primary leaving group. All right, that wraps it up for the E2. What's next? The E1 mechanism. I'll see you then.